This is part 5 of the series Similarity, and in this part we're going to start out by looking at two related theorems. And the first theorem is the triangle proportionality theorem, which says if a line is parallel to one side of a triangle and intersects the other two sides, then the line divides the two sides proportionally. And the idea here is that this line, because it's parallel to this third side, creates two similar triangles, triangle ADE and triangle ABC. And because those two triangles are similar, then by definition the corresponding sides must be proportional. So that's the idea behind this theorem. The converse of this theorem states that if a line divides two sides of a triangle proportionally, then the line is parallel to the third side of the triangle. So this goes in the opposite direction. If we have this dividing these two sides proportionally, then these two triangles must be similar polygons. Now I'm going to go ahead and offer a proof of the triangle proportionality theorem because I think it's a nice little exercise to hone our proof skills and our knowledge of theorems, definitions, and postulates. So let's go ahead and do that. So here we have our picture. We have triangle ABE, and we've got line CD that is parallel to AB. And that's our given, so we've written that down already. Now the general plan for our proof is we're going to try and show that triangle CDE is similar to triangle EBA. We know that we have a shared angle here, and since these segments are parallel, we have corresponding congruent angles. So we should be able to show that these two triangles are similar by angle-angle similarity. And then hopefully we can make some substitutions in our proportion that we create because of the similar polygons. So that's the general idea for the proof. To start off, our first statement will be that angle E is congruent to itself by the reflexive property of congruent angles. Our next step in showing that these two triangles are similar will be to show that these two angles are congruent by the corresponding angles postulate. So now that we have two angles of one triangle congruent to two angles of a second triangle, we know that these two triangles are similar by angle-angle similarity. Now that I know these triangles are similar, I want to set up a proportion to get us one step closer to creating this proportion here. So the proportion is going to be this is to this as this is to this, and see where that leads us. So we're going to say CE is to BE as DE is to AE. So now we have our proportion, and the reason for that was the definition of similar polygons, that in similar polygons all corresponding sides are proportional. So now let's move on and see if we can't generate some relationships between these segments that will get us one step closer to matching this proportion. Right now we've got a CE and a DE, but we don't have BC and AD. We have this BE, this whole segment here, and we have AE, this whole segment here. So what I want to do is rearrange this a little bit, and then we're going to make a substitution using the segment addition postulate for this segment and this to get our segments BC and CE, and then AD and DE. So the first thing I'm going to do is I'm just going to cross multiply these two to get rid of the proportion so that I can do a little bit of math inside this relationship. So we're going to multiply CE times AE equals BE times DE. So we've cross multiplied and got this, and we used the multiplication property of equality to do it. Now, because of the segment addition postulate, we know that AE is AD plus DE. So we're going to write that here, and we know that BE is BC plus CE. So let's go ahead and write that in. So now we have AE is AD plus DE. BE, this whole segment, is BC plus CE. Now we're going to perform a substitution. We're going to substitute this in for this and this in for this. And that's going to give us a new relation for this. And we're going to use that as the substitution property of equality. So again, what we've done is we've taken this AE and substituted it for this version of AE right here. We've taken this BE and substituted it for this version of BE right here. Now if you'll notice, if we distribute the CE throughout these two and distribute the DE throughout these two, we're going to have a CE times DE on this side of the equal sign and a CE times DE on this side of the equal sign. That's going to give us something that we can subtract out, and we're going to have a proportion that's going to look similar to this. Let's go ahead and distribute these terms. Here we have the product of CE times DE on the left side and CE times DE on the right side, and these guys will subtract out. So let's go ahead and do that and subtract these from both sides. So here we've subtracted CE times DE from both sides, and we're left with CE times AD equals DE times BC. And now you'll notice that we have a CE and an AD on one side, and a DE and a BC on the other side. So we have all the four pieces that we need. We just need to get them into the proper proportion positions so that we have this final proportion. So we have AD that needs to be in the numerator. So what I'm going to do is I'm going to divide both sides by CE. And if you notice, since AD is here, and if I divide this by AD on both sides, the AD is going to disappear from the left side and go into the denominator on the right side. And that's exactly what we need. We need the AD in the top and the CE on the bottom on the opposite side. Likewise, we have a BC on the top, and that's what we need. And we're going to divide both sides by DE. So if we divide both sides by DE here, the DE is going to disappear from this side and appear in the denominator of this side. So we're going to do two steps in one. We're going to divide this side by CE and this side by DE. So let's go ahead and do that and see what proportion it creates. So here we divided by CE. Notice the CE's disappeared on the left and it's appeared in the denominator on the right. Now we have BC over CE, which is exactly what we need on one side of the equal sign. But now we got to get rid of this DE. Since we're multiplying by DE, we're going to do the opposite and divide by DE on both sides. So let's go ahead and do that. And here we divided both sides by DE, so you can see DE disappeared from the right and it appeared in the denominator on the left. Now we have the proportion we're looking for. We've proven that AD is to DE as BC is to CE. So given a line parallel to a third side of a triangle, it divides the two sides proportionally. So BC is to CE as AD is to DE. Now it's possible to alter this proportion in any of the standard ways. We can exchange the extremes, we can exchange the means, we can take the reciprocals of both sides, and we can swap them from left to right and still have the same proportion. So that's why these are an easy theorem, because it's very visual. If you were to draw a line through this, you could see that this is to this as this is to this, or this is to this as this is to this. Go backwards, this is to this as this is to this, and so on. Any of those are valid proportions because this line divides this side and this side proportionally. Let's go ahead and put this theorem into practice in a practical example. So in this example we have OE is parallel to GE, and therefore by the triangle proportionality theorem, it divides this side and this side proportionally, and we're looking for GE. Now the way I like to do these is I like to set up my proportion with my unknown on the top left, simply because it makes it easier to manipulate algebraically. So that's what I'm going to do. I'm going to put my unknown up the top left, so x is 2. Now I can do any proportion I want. I can say this is to this as this is to this. I can go in this direction, this is to this as this is to this. It really doesn't matter. It all works out the same. So I'm just going to make it clean and say this is to this as, come back here, 32 is to 24. And that's all I have to do is multiply by 14. So x equals 32 times 14 divided by 24. Put that in our calculator. We get 56 thirds, which is 18.66 repeating. And if you want to check your results, you can take 56 thirds and divide it by 14, and you'll get 1.3 repeating. If you divide 32 by 24, you'll get the same ratio, 1.3 repeating. So let's move on to the next example. Here we have a similar example, and this time we're looking for AD. And as you notice, it almost sets up its own proportion visually. This is to this as this is to this. You could do it another way, but why make life difficult? I like to put my variable in the upper left. So again, x is to 23 as 8 is to 10. Multiply both sides by 23. X equals 8 times 23 divided by 10. Put that in our calculator, and we have 18.4. So if this is 18.4, if we divide 18.4 by 23, so 18.4 divided by 23, we get 0.8. If we divide 8 by 10, you can see that we get 0.8. So just a little cross-check to make sure that we've done it correctly. We can see that these are in fact proportional. So let's move on to the next theorem. This next theorem doesn't relate to triangles, but it is a proportionality theorem, and it's very similar in nature to the ones we've already studied. It's the three parallel lines theorem that says if three parallel lines intersect two transversals, then they divide the transversals proportionally. So if L is parallel to M, which is parallel to N, then AB is to FE as BC is to ED. And again, we can create any number of other proportions, AB to BC, FE to ED, and so on. Let's go ahead and look at a quick example and put this into practice. Here we have three parallel lines cutting two transversals, and we're looking for this entire segment from P to R. So the first thing we need to do is find QR. So X is to 250 as 162 is to 180. Could create any number of proportions, but that's the easiest for me. X equals 162 times 250 over 180. Putting this into our calculator, we have 225. So this value is 225. 162 plus 225, PR equals 387. So a fairly basic example, but it gets the idea across. Let's go ahead and move on to the next theorem.